Hi everyone, welcome to our discussion for today. Today we are going to tackle the topic implicit partial differentiation. So for example, find the slope of the sphere given in this equation x squared plus y squared plus z squared equal to 1 in the y direction at the points with these coordinates. So these are x, y, z coordinates and for this point with these coordinates as shown in this picture. So it means that for this point, these, uh, these are the coordinates. For this point, these are the coordinates. So we're asked to find the slope. Okay, so slope of the line. All right, so we're asked to solve for the slope. Okay, so the point, this particular point here, this point with these coordinates lies on the upper hemisphere. So it's in the upper hemisphere of the given sphere. Uh, Given into this equation, z is equal to the square root of 1 minus x squared minus y squared. All right, so this is the function, or this is the equation of the given hemisphere in the upper part. So z as a function of x and y, so given in this expression. And at the point, so at this point, all right, lies the lower hemisphere. So this lower hemisphere of the sphere is given by this equation, z equal to the negative square root of 1 minus x squared minus y squared. So we could find the slope by differentiating each of these given expression for z separately with respect to y. And then after that, evaluating the derivative at x equal to 2/3 and y equal to 1/3. However, it is more efficient to differentiate the given function, right? Given in this manner, meaning you transform this into an expression without the radical. All right, you just manipulate this one, square both sides, then after that transpose this x squared, negative x squared and y squared to the other side, and then putting 1 on the right side. So we have this equation that is taken actually from this. All right, considering the positive part of it, okay, because we have also the negative part. So it means this corresponds to this one, okay, and the other one, if you take the negative part, so meaning this slope, okay. So we are going to differentiate this implicitly with respect to y, since this will give us both slope with one differentiation. So to perform the implicit differentiation, we view z as a function of x and y. All right, so z, if you see here, there are only two variables on the other side, so we can see that z is a function of x and y. All right, taking x to be fixed. So if you're going to differentiate both sides with respect to y, okay, differentiating both sides with respect to y, and then we'll we're going to hold x as constant, then the competition will follow as this. Now, after differentiating it implicitly, so this becomes like this. So differentiating partially both sides of the implicit function. So we have this. So as we differentiate this implicitly with respect to y, so we hold x as constant, right? So we hold x as constant. Okay, so when x is constant, all right, class, I will not write the whole word. I'll just say to refer it to constant. Okay, so differentiating partially with respect to y, holding x as constant. So we have here partial derivative of this. This is constant, so this is 0. So derivative of this y squared, that is 2y. Then partial derivative of this z squared, so use the power formula. So 2z times the derivative z, partial derivative of z with respect to y, and then partial derivative of the right side, which is constant 1, so that is also equal to 0. So therefore, we can solve for partial derivative of z with respect to y. So just transpose this to other side, all right, and then they divide both sides by 2, so it gives us this result. Partial derivative of z with respect to y equal to minus y over z. So this is actually our slope, right? So substituting y and z coordinates of the points. So these points here, I mean these points, these 2 points, this point and this point. So this one correspond to this point here, okay? Okay, so this corresponds to this point. And this one here, 2 1 1/3 and minus 2/3. Sorry, this one is for this, all right? And this is for this point here. Okay, so when you substitute the value of y and z coordinates of these given 2 points in this expression, all right, so we'll be able to solve for the slope. So we will be able to solve for the slope. So therefore, the slope at the point, meaning at this point here, okay, so at this point with these coordinates is equal to 1/2 when you substitute here, because you have y, so take the value for y and also for z. Okay, so the value for y. Okay, so y here, this is this is our x value. Okay, then the second number, this is our y, and the third value is for z. Okay, so substituting those values, then we'll be able to get for the slope. So for this point, meaning the above the point above the hemisphere or the upper hemisphere, so this is equal to negative 1/2. Okay, so if you look at the line that is sloping downward to the right, so it means this is negative 1/2, so that confirms our result, that is negative. And if you look at the value for the slope for this point after substituting the value of y and z, so for this particular coordinates, so this is for y, okay, this is again, this is for x, this is for y, and this is for z. So substituting this, okay, when you substitute this value to our result here, okay, because this is our slope, all right, so we get 1/2. Okay, 1/2, because 1/3 divided by 1/3 divided by 2/3, so 3 divided by 3, so that is 1. So we have 1/2, negative 1/2, but this is negative here, so this makes the result positive 1/2. Okay, so that's it. That's the application of the partial differentiation. So when you're given a function that is in implicit form, or you're given an expression that is in radical form, and they transform it into something that can be written in this manner in implicit form, and then use the same concept in differentiation that we've learned before, the implicit differentiation, and then the derivative that you will be obtaining there is the slope, no, slope of the line. Okay, so thank you very much, class. I hope you learned something from this part of our discussion. Okay, bye, and see you in the next video.